Emerson's dedication to environmental protection is to early prediction of flare events based on analytics and big data. So the agenda of today's talk consists of 4 parts. First, background, I will briefly talk about the flare gas recovery system, which we are studying, and also the method we leverage, which is based on analytics and big data. And then there's actions part, which we will take to alert the process operators. Finally, I will conclude the presentation. So here you can see is a typical flare gas recovery system, and the flare gas is going through a, cannot see here, a drum here, and if the pressure of this flare gas is above certain kind of limit, so this flare gas will be released and being sent to the flare stack to be burnt. In that case, we cause a severe event. We will release a significant amount of greenhouse gas in the atmosphere. So it's quite an undesirable event. So we need to mitigate such a problem. So the objectives of this project is threefold. First, we want to avoid or reduce flare events. The second one is that we want to predict conditions that lead to those unwanted flare events with enough lead time for the operators to act. Typically, it's at least 15 minutes before this flare event. The third one is to provide operators with indicators showing units which are causing those flares. So, but we face quite a few challenges. So you see, in a typical petrochemical plants, we may have more than, for example, 18 units which can cause those flare events. Also, we are dealing with a dynamic system, and it's also a multi-modal, means the process is operated at different modes. And also, we are dealing with high-dimensional process data, and it can be really noisy and oscillatory. And the problem, another challenge we face is that the number of flare events we can analyze is quite limited. So it's kind of finding a needle in a haystack. So here shows available process data set, 1 year of process data. You can see there's hundreds of thousands of data points, and for more than 100 process variables. And also I highlighted the time points where the flare event occurred. There's for a year, the flare event occurred around 10 times. So you see this one is the process data is high dimensional. There are more than 100 tags of process variables, and they may include the pressure data, temperature data, and flow rate data. So in order to predict the flare event, a preliminary step we conduct is trying to understand the process. So we plot the sum of scale flows and also the stack pressure into a single plot, and it's easy to observe that this periodic behavior is observed, which corresponding to a daily heating and cooling cycle of this plant. But if there is a flare coming, you see this such a oscillatory behavior is disrupted. As you can see, it's no longer regular, as showing this in nice cycle here. Such cycle is being disrupted. Then there's a flare event shows up. So based on such observation, we think, oh, because there is a nice regular oscillatory behavior, maybe we can do something to predict. So first approach we did is to use a moving window fast Fourier transform to analyze those oscillatory cycle. Then we generate a new time domain variables of frequency and magnitude, and we filter this variable with the principal components. And turns out we can successfully predict 5 out of 14 those flare events. But we are not quite satisfied with the result because there's like 9 more. We are missing 9 more flare events, so we need to do better. So then we work on to improve our approach. We develop a hierarchical and hybrid approaches. The hierarchical aspect states that we're looking for signals in each of those 18 units separately, and we will combine those signals for overall index. And we want to avoid one or more units, like we're swapping the effect of other units. Because after we detect the flare event, we need to find out which unit is likely to be the cause of this flare so that we can notify the operator saying, okay, you need to take some actions. Then for the hybrid perspective, we will use both time domain and frequency domain approaches, and we combine them together. And we will add slow feature analysis by including variable derivatives as additional variable. So some of the terminology here, like we use, first is PCA stands for the principal component analysis. The DPCA is for dynamic PCA, principal component analysis, which is PCA, but accounting for time lags. Also, WT stands for the wavelet transform. It's similar to the Fourier transform, but it's in a wavelet form. And also SFA stands for the slow feature analysis, including derivatives of the process variables. And H stands for the hierarchical. So we proposed a distributed monitoring framework. This one shows a unit-wise level. Basically, we collect the data for each unit, and we detect based on those data, and we will do some analysis for each unit to monitor the flare, to help us to monitor the flare. So one benefits of this level is that it can help us to isolate those flare causes. The next one is the hierarchical level. You can easily compare between this one and the previous one. We can, in this case, we kind of combine those data from different units together and through a dynamic PC or slow feature analysis, and we can generate a detecting metric, so that it will help us to easily to monitor the flare data overall, so that help us to reduce the false alarms or predict the flares. So here's the results. You can see this this shows t-square statistics plot, and the red bar is the time period corresponding to the actual flares. And this t-square, which is showing the black line here, and you can see clearly in several of them there is a peaks at some time, actually like at least usually like at least 10 hours before those flare actually occurs. That means we can clearly predict or correctly predict when the flare occur. So overall, we summarize the results in the table here. You can see the results the method we proposed can actually correctly predict 11 out of 14 flares, which is a significant improvement from previous one, which is only give us 5 out of 14. So after we successfully predict the flares, we need to notify or inform those operators to take actions on them. But we need to do some prep work for those operators, and this is what we're going to do. First is to interview subject matter experts to derive the requirements for long lead event detection during process monitoring. And then the second one is we need to, from our perspective, we need to design a certain human-machine interface so that all the operators can be notified. And the third one is assessment, is to work with those experts to assess the human-machine interface, the quality of those HMIs. So this slide shows the L1 display of the human-machine interface we use that will alert operators to potential flares. You can see this little yellow rectangle on the top right, and the yellow is a warning sign over there. And all operators will be alerted to this problem. In that case, all of them they don't need to be notified or told by a single operator, which is only in charge of monitoring this flare gas recovery system. So all operators will be notified, will all communicated to take action. So the operator can also drill down to the level 2 HMI to find problem source. In this case, by interviewing with the operators as a prep step, we already know there are 3 likely causes of such flare. In this case, showing in this table, this CCR, like the CCR unit, or this hydro cracker unit, or this special chemical unit, and out of which the main cause of those flares, main contributor of this flare is likely to be the CCR unit. But there is still the results give us an unplanned cause of this flare, which we need to discuss with the operator to see what's going on there. So the conclusion of this topic is that you can see in this project, we develop a general distributed monitoring framework to predict the flare event in the petrochemical plant. Also, this approach incorporates both time domain and the frequency domain method to help us to improve the prediction accuracy. And also, our results are quite good, and it gives us 11 out of 14 early predictions. And also, based on our results, we also design HMIs for notifying operators through L1 and L2 displays. So that concludes my presentation today. If you have more questions, you are welcome to visit the booth 14315. And